Hi, everybody. I'm going to go over the last two homeworks and see how it all goes. Hi, Bruce. I'm going to go over the last two homeworks. I'm going to start with the homework from chapter 15 and then go through it all. Just let me know in the chat if you need anything. It's being recorded, so if you need to go. Oh, I'm sorry. I'm going to start with chapter 12. Chapter 12, if it will ever load, was all about torque and equilibrium. And we'll review some of that. We'll load. All right, so this first question is about basically understanding angular variables. Don't forget, way back when we first did rotation, that we have the following variables: theta final minus theta initial is omega t plus alpha. We have omega final minus omega initial is alpha t, and we'll use this one. And that's for constant torques or constant angular accelerations. We also have the following, that one revolution is 2 pi rad. We're going to have to convert in this problem from RPM to angular acceleration. So a rev per minute, we need to turn into a rad per second. And how we do that is there are 2 pi rads per rev, and there are, in 1 minute, 60 seconds, and I'm told at least, sorry, where'd that problem go? I'm told at least on mine that I start with 2,000 RPMs and 0.54 seconds. 2,000 RPM and 0.54 seconds. To turn this, I need to multiply it by 2 pi over 60. Now I'll put it in omega. This is actually my omega final. It's 2 pi divided by 60. I get 209. So my omega final is 209.44 rad per second. And I'm assuming that at the beginning, omega initial is 0, that I started from rest. So I went from 0 to 209, and I need to get alpha. I also have t. So I just need to use this one. Omega final minus omega initial is equal to alpha t, divide through by t, and you get alpha. This is 0, so alpha is 209.44 rad per seconds over 0.54, which divided by 0.54 seconds is 388 rad per second squared. Make sure that's right. 388 rads per second squared. How many revolutions does it turn? Now, we need to figure out, one revolution is 2 pi rad. So we need to find the change of angle. We know what alpha is. Alpha is 387.85. 387.85 rad per second squared. And from that, hi Lyra. The only thing I've done so far is in the first question, I had to use these. These are the constant angular acceleration. From those, I had to convert from RPMs to radians, and then I use this equation to find alpha. In this next one, they're asking us how many revolutions up in enough time. So we know from the first part that omega initial was 0, omega final was what we got in rads per second, 388. And we are recording. the time was 0.54, and what I'm trying to find is the change of angle. So knowing that, I can come back and look at this and get this change of angle. So what we get here is omega final squared minus omega initial squared is 2 alpha times theta final minus theta initial. This is what I want to solve for. Divide both sides by 2 alpha. Now, once I get this, this will be in radians, and they want revolutions. So I need to divide by 2 pi rads to get the number of revolutions. So, this goes away. I get 388 squared over 2 times, sorry, this was 209.44. I'm done. 209.44. 209.44, and this was 388 points, or 387.5. I'm just going to use that. 209.44 times 209.44 divided by 2 times 388. I get 56.527 radians, 56.527 rad. But I want revolutions. There are 2 pi rad per revolution, so divide that by 2 pi. And we get 9. There are basically 9 revolutions. I get 8.999. So 9.0 if we round. So this whole problem is about converting from RPM to radians per second. And you do that because this is revolutions per minute. So this is revs over minutes. The conversions are, there are 2 pi rad per revolution, and there are obviously in 1 minute, 60 seconds. The rest of this is all about using those. I just wanted to make sure you all didn't forget that you have those equations. So when we have constant torque, we have constant alpha, and we can use them. All right, a car tire is 55 centimeters in diameter, and the car is traveling at 18 meters per second. What is the tire's rotation frequency in RPMs? So we have this tire and it's full diameter. We're probably going to actually want R, but its diameter is 0.55, 55 centimeters. And we're told that its velocity is 8 meters per second. Hi, Angel, we are recording. So R is half of the diameter, or 0.275 meters. And omega is R, I'm sorry, take that back. Don't forget that the arc length S is equal to R theta. V is R omega, and A is R alpha. So they've asked us for omega, but they want it in RPMs. So R omega is V over R, and that's 18 over 0.275. But this will give us rads per second. And what we want is we want to turn that into revolutions per minute. So there are 60 seconds in 1 minute. And there are 1 rev, 2 pi rad. So what we need is 18 over 0.275, 60 over 2 pi. And I get 18 times 60 divided by 0.275 times 2 times pi. I get 625 RPM. I'm being dyslexic. 625. Okay. What is the speed at the top of the time? Now, they go over this in your book, but I've basically gone over it here. If we assume rolling without slipping, so we assume V is R omega, that means that you will have V from translation for all 3 points. And then you'll have V from rotation in the same direction at the top, in the opposite direction at the bottom, and you will have no V there due to rotation. What this means is the top of the tire is going to travel at double V. The center of the tire is going to be traveling at V, and the bottom is going to be stationary. So V was 18. This is 36, obviously, for the top, and the bottom is 0. If they asked about the center, it would be 8. All right. The reason for that is that it has rotation as well as translation. All right. So the net torque about this axis, we see that we have a force on the top and a force on the bottom, and we have a diameter of 4 centimeters. Whenever we draw torques, our axis of rotation here is the center of this wheel. And we see that it's helpful to draw it like this first, R, the top one. And this force was 30 newtons. And then we also have an R to the bottom one. And this force was 20 newtons. And our diameter was 0.04 centimeters. So our radius is half of that, 2 centimeters. And that's the same for top and bottom. All right, but we need to draw a torque diagram for each one of these. So for the top one, draw them tail to tail, force is 30. R top, which is 0.02. 0.02. Now we curve R to F, and in our class or in our homework, they always assign clockwise as negative. So this is negative alpha. For the second one, I have a force of 20 newtons. I don't know why I was wrong with my fingers tonight. And R to the bottom, but this is also 0.02 meters. Turning this one to F, we see that we're rotating counterclockwise, and this one's positive. So our net torque is these two. They're 90 degrees off each other, so we don't have to worry about the sign. Normally, torque is R sine angle between R and F. I'm going to turn somebody off. I'm going to turn you off, Angel. I can hear you. These two are both 90 degrees. What are you growling for? And therefore, this one's negative because it's rotating clockwise. The second one is positive because it's rotating clockwise. So I'm going to start with the 20 Newton force, which is at 0.02. This is R, this is F, minus the 30 Newton force, which is also at 0.02. So what I see here is I get 20 times 0.02 minus 30 times 0.02. And so I get a net negative torque. This would be 0.4, this would be 0.6, so I get negative 0.2. And the units would be Newton meters. Okay. So that's why we got a 0.02. And they do want the sign. They're taking the sign to be clockwise as negative. Okay. So just make sure that on this, you can draw these torque diagrams, and then you can write the net torque equation. This is incidentally also equal to I alpha. But so it's R is 0.02 times 30, but that one's negative. R is 0.02 times 20. This one's positive because it's clockwise. All right. So that one's not too bad. Now, we have a 1 kilogram ball and a 2 kilogram ball connected by a 1 meter long rigid massless rod, and the rod is rotating clockwise is what that means, about its center of mass. Okay, so what we need to figure out is first, and I talked about this one, but we basically have these two balls, and these two balls are along a 1 meter. This one's 1 kilogram and this one's 2 kilograms. This is along a 1 meter rod. I'm going to say that this is 0. So this X is 1 meter. I need to find the center of mass, and how I do that is M1 times its center of mass, M2 times its center of mass over their joined center of masses. M1 is 1, but X1 is 0. M2 is 2, and X2 is 1, and this is 1 plus 2. So I get 2 over 3, or the center of mass is at 2/3 of a meter. So like here somewhere. They're going to rotate around that. Now, we want to know what torque will halt them in 4.4 seconds. And what we know is that they're spinning at 19 RPM. Now, if we go back and we remember, let's turn this back into rads per second. This is revolutions per minute. So I need to multiply by 2 pi rad over a rev. And I need to multiply by 60 seconds in 1 minute. Sorry, I flipped that one. It's per minute. So RPMs mean rev per min. So in 1 minute, there are 60 seconds. And this is my omega initial. So 19 times 2 pi divided by 60 is 1.9896. 6 rad per second. My omega final is 0. They want to know, I want to bring it to stop. Now, in order to do that, we want to stop it in 4.4 seconds. So what we're going to need to do is we need to find the net torque, or I'm sorry, not the net torque. We need to find, the net torque. We need to find the net torque that will stop this thing. But torque is I alpha. Now, I, for 2-point masses about the center of mass, is mr squared. But for number 1, R1 will be 2/3 of a meter. R2 is going to be 1/3. How far they are away from where they're rotating. All right, so I is M1 R1 squared and M2 R2 squared. This was 1, this was 2/3 squared. This was 2, and this was 1/3 squared. So this is 4/9, 4 over 9. This is 2 times 1/9. So this is 6/9 kilogram meter squared. Then we have to find alpha. In order to find alpha, we know omega initial, omega final, and T. Omega final minus omega initial was alpha T from the very beginning. So alpha, since this is 0, is going to be negative omega over T. Divide both sides by T. This is 1.9896 negative, and T was 4.4. So my alpha negative 1.9 divided by 4.4. I get negative 452 for alpha. Alpha is negative 0.452182 rad per second squared. And the net torque needed will be I alpha, so 6/9 times negative 0.425452,182. I multiply that by 6/9, and I get negative 301.301 Newton meters. They just want the magnitude, so they're taking the opposite value, so negative doesn't need to be there. Again, to find the center of mass, we won't have to do this on the final, but for anything, m times x, where x can be y, z, whatever, m total, so sum all the m's, and then each of the individual coordinates, etc. So what we did was we did that, but we chose 0 to be on the first one. We wrote that. We ended up getting the center of mass was at 2/3. Then to find the torque, we needed the moment of inertia. The moment of inertia for a point mass, which is what these are, is mr squared. This one's r. It's 2/3 of the way away from where it's rotating. This one's 1/3 of the way. And so this m times 2/3 squared and this m times 1/3 squared. That gave us our I. We got alpha because they gave us omega initial, omega final, and T. So hopefully that all makes sense. All right. We're now doing equilibrium. And in equilibrium problems, all the forces in X, all the forces in Y, in fact, all the forces in Z are 0. And the torque about any axis has to also be 0. So our goal is to find whatever we're looking for somehow by using one or more of these equations. I usually start off drawing the forces, but we're told that this thing is 3 meters long. There's 2 stands, one on either side. And there's a 94 kilogram, the beam is 94 kilogram, the student's 720, and he's 2 meters away from support 1. And we want to know how much force does support 1 exert. Looking at this picture, okay, these 2 things on either end are normal forces. I'm going to call them normal 1 and normal 2. In fact, I think I have that backwards. Nope. That's what they did. Everything we consider uniform. So at the center of this rod, we're going to have the mass of the rod times G. And where the student is, although it doesn't matter, well, the mass of the student times G. And those are the only 4 forces on you. However, if I write the force in the Y, I would get N1. So the sum of the forces in Y is 0. And it's N1 plus N2 minus MRG minus MSG. And I don't know N1 or N2. I can figure out MRG and MSG because they gave me my masses. I need to use the torque equation. Now, I'm going to choose an axis that's going to make my job easier. And that axis is going to be right here. If I choose this as my axis, I don't have to worry about N2. So what we'll do is we now have about this end, we have, this was at 2, the mass of the student G. So this distance away is 1 meter. We're starting from here, and we know the rod is 3 meters long. Since the student is 2 meters away from support 1, he is 1 meter away from our axis. Now, the second force, which is the mass of the rod G, that's at 1.5 meters. Again, the rod's 3 long. And then our final one is N1, and that is the full length away. So R is 3 meters. If I draw these things tail to tail, I'm going to draw 3 separate torque diagrams. I have R is equal to 1 meter, and that is the mass of my student. R is equal to 1.5, and that is the mass of my rod or board, whatever you want to call this thing. And then finally, N1, and that is R is 3 meters. Turn each of the R's to their force. And then just note whether or not they're positive or negative. I'm going to call counterclockwise positive. It doesn't matter which one you call positive, you just have to make sure all the forces that are that one are positive and all the other ones are negative. The reason why is the sum of the torques is 0. We can move it to either side of the equation, all the signs would flip. So this one is R student MSG, they're 90 off, plus R of the rod, M of the rod G, minus R of the normal force times the normal force. I want to find N1, move that over. So I get R N1, RS plus RR. divide through by r normal, how far away it is. And what I get is the following. My student is 72 kilograms. Yours is probably different. So this was 172 and 9.8 plus 94 for the rod. And it's 1.5 and it's also 9.8. And I know I'm running out of room here. Sorry. So times 9.8 and then divide this whole thing. Yeah, I'm just gonna rewrite it over here. So N1 is R, the student was 72 and 94. So 72 times 1 times 9.8 plus 94 times 1.5 times 9.8. And I switched R and MRG. And this was 3. So 72 times 9.8 plus 94 times 1.5 times 9.8. I didn't forget the 1, I just didn't put it in my calculator because it's 1. Divide by 3 and I get 696 newtons. So they rounded completely up to 700, which is fine. They rounded to 1 sig fig. I don't know why they rounded to 1 sig fig when they really have 2 there. I guess they could put 7.0 times 10 to the second, but they rounded up. Otherwise, we would get the same answer. Now, how much upper force does support 2? Well, if this one is 696, and my rod was 94, and my student was 72, and then N2, move N1 over, and move both these over, is M of the rod plus M of the student minus N1. And that's 94 times 9.8 plus 72 times 9.8 and minus 696. Don't put 700, I think you'll get it wrong. 94 times 9.8 plus 72 times 9.8 minus 696. And I get 931, or maybe you won't. 931 newtons. They get 930 because they didn't. I get 930.8. They're saying 930. Again, 2 sig figs, that would be 2 sig figs would be 9.3 times 10 to the second. All righty. So the main takeaway here is you write the force equation in the X, the force in the Y, and then you can put a torque equation with an axis and we want, which will help you eliminate something. And then you just kind of go through them. All right. A solid sphere is rolling, and this thing's rolling. So when something rolls, it has kinetic energy, mv squared over 2, plus energy of rotation, I omega squared. So we want an expression for the kinetic energy only in terms of m and b. We need to turn this into m and b. I for a solid sphere is 2/5 m r squared. Omega, if we remember, is v is r omega, then omega is v over r. So if we plug that in, what we get is we get 2/5 m r squared all over 2 times v squared over r squared. The r's cancel, one of the 2's cancels, and I get mv squared to the 5th. The total kinetic energy is mv squared over 2 plus mv squared over 5. They multiplied by 2 over 2. So what they got, I don't know why they did that way. They wrote it that way so that they could write it nicely, but you could write it like this. You could probably write it, multiply this by 5/5 and this by 2/2, and you would get 5/10 plus 2/10. So you get 7/10 mv squared. I think they did it this way so that you can see the kinetic energy and then the extra part. But the answer is that you have kinetic energy of rotation when you're rolling. You can change omega into V's, and you can eliminate the R's that way. So now we want to know if a 2-centimeter diameter marble is shot up a 15-kilogram ramp at 3.0 meters per second, how far will it travel? We're assuming this thing's solid. So, all right, we're going to need to do the following. We have a ramp. We have this ramp. And they want to know a 15-degree ramp. And this thing's got an initial V of 3 meters per second. So its initial kinetic energy is going to be 7/10 mv squared. That's going to be its energy here. Somewhere up here, it's going to get to mgh. Okay, so somewhere up here, we're going to reach mgh. At that point, it's not going to have any rotation, any velocity at all. However, h here, h is d sine theta, and we want d. So what we get from energy is the energy at the top will be mg d sine theta, and the energy at the bottom will be 7/10 mv squared, setting those things equal to each other. mv squared plus r equals mg d sine theta, divide through by mg sine theta. Sine theta. And I get, the m's cancel, I get 7/10, sorry, d is equal to 7/10 v squared over g sine theta. 7/10 times 3 times 3 is 9, divided by 9.8 times sine of 15. I get 2.48 meters, or 2.5 if you round. So here's the thing. When we do energy, when we have rolling, at the bottom here, it's going to have mv squared 2 plus I omega squared over 2 plus mgh. And then at the top, so call this the bottom, and the bottom, and the bottom. And at the top, it's going to be mv top squared over 2 plus I omega top squared over 2 plus mgh top. However, by using the appropriate moment of inertia, which will always be something mr squared, we can actually turn these into mv squares, which is what we did. We turned this into 7/10 mv top squared, and we turned this one into 7/10 mv bottom squared, or yeah, mv bottom squared. I have that flipped, sorry. Top, bottom flipped. Top, bottom, and top. Plus mgh bottom plus mgh top. Now, when it gets to the top, wherever the top happens to be, it stops. So it doesn't have any of that energy. So we're setting the energy at the bottom to the energy at the top. There's no spring. We also will assume that HB is 0 at the bottom. And the last thing we have to do is note that H at the top is D sine theta and solve. Pretty simple. Not too bad. All right, back to ladders. Now, we talked about ladders. Ladders are essentially always the same. You have a normal force in the X off the wall where they're touching. So we have a normal force here. We have a normal force on the floor upward where they're touching. We have to have a force of friction here, which will be mu y, and at the center of the ladder, we have the mass of the ladder times g. If we rewrite these as forces, sum of the forces in the X, 0 is equal to nx minus mu and y. Sum of the forces in the Y are 0, ny minus mass of the ladder g. We want to know what minimum angle can we make to the floor. Notice there's no angles here. We're going to actually have to get a torque equation. Now, in order to get that, we need to do a couple things. We're going to set our axis of rotation here. And when we look at this, so if we look at this here, we have up the ladder half the length, mlg. And then all the way up, we have nx. So what we get here is, remember, RF sine of the angle between R and F. For nx, you put them tail to tail. We don't know what this angle is, but we know that this angle, the angle that goes from our R, which is L, to nx, is 180 minus theta. We could also rewrite this as cosine of, or I'm sorry, sine of theta, if we wanted to. I'm not going to do that right now. I'm just going to leave this angle here. For my second torque, and I'm going to call this torque negative. For my second torque, I have L to the half and then mlg. And this angle is theta plus 90 degrees. So my torque equation is 0, this one's positive, is 0 L to the half mlg sine of theta plus 90 degrees minus L and x sine of 180 minus theta. Now, that is almost impossible to solve for theta without doing some crazy trick. So I'm going to show you something on this one, okay, where we have nx and we have L. And this is our axis. Instead of L, which is at theta, I'm going to use this. This is L sine of theta. And nx is this way. So I'm going to use the fact that these guys are 90 degrees off, and this torque is therefore L sine of theta and x. For the other one, I have L to the half, and I have mlg. Well, here I'm going to use this part. And this, since this is theta, this is L to the half cos. So this torque is negative L to the half cos. The angle between them is now 90 degrees. I can always find the perpendicular part of my lever arm instead of trying to find the angle between them. If I write my torque now, 0 is, this one was negative, this one was positive. I flip the sign, it doesn't matter. And x minus L to the half cos mlg. Move that over. And what we get is the following. L to the half cos mlg is equal to L sine nx. The L's will cancel. I'm going to move the cosine over. So that's going to go away. So this is 1. Actually, what I have now is mlg over 2 is equal to tan theta and x. All right, move nx over, divide through by nx. And my angle is the arctan of MLG over 2nx. Now, I don't know what nx is, but if I go back and look, nx was equal to mu ny. Move that over. But ny was equal to mlg. So this is mu mlg. I'm going to put this back in here. This becomes mlg over 2 mu mlg arctan. Or this goes away, and what I get is the arctan of 1 over 2 mu. Mu is 0.48. So arctan of 1 over 2 times 0.48. I get 46.2 degrees. Or 46 degrees. Okay, so going back on the ladder, we have nx because there's a normal force. There's no friction on this wall. We have ny and a mu nx or mu ny. And we always have to have a weight. When we do that, we get these two force equations. However, we don't have enough information to solve it because we don't have an angle. So in general, what we then do is we take the torque about this axis. When you do that, you'll end up with these two equations. However, this is messy. Instead of using sine, what we can always do is find the perpendicular part of the lever arm to our force. And so when I look here, the perpendicular part is L cos theta. And when I look here, L sine theta. The perpendicular part is L cos theta, L to the half cos theta. And now L sine of theta is increased to nx. So this just becomes L sine theta nx. And this one becomes L to the half cosine mlg. You can always do that. You almost never have to because you usually have the angle. But if you don't have the angle, sometimes that works better than trying to do it the other way. There are other ways to do it. All right, now we have the sine problem. So there's scaffold problems, which we did that first one with the two supports. There's ladder problems and then sine problems. And on a sine problem, you almost always have a rod with some kind of wire. It might be up, it might be over. In this case, it's here. And when we look at these forces, there's always a force upward at the wall. So let's call it a force Y, and there's a force in the X. Here, whatever angle this happens to be, there's a tension times cosine of the angle, and there's always a tension times sine of the angle. That's this tension force is decomposed. And then finally, the center of the rod, there's always a weight. In this case, we have a extra force. We have a gentleman, and our angle is 30 degrees. So we have, at some point, some man. And we know that our angle is 30 degrees. All right. And he is 1.5 from the end of a 6.5 rod. So this is going to be 1.5, and the whole thing is going to be 6. And the beam itself is 1450. Right. And the man is 90. So what is the tension in the cable? Let's start by doing our forces. In the Y or in the X, I have Fx minus T1 cos theta. If I knew Fx, I could solve this for T1 because I know the angle. 0 is the Y forces, and I have Fy plus T1 sine minus Mr minus the mass of the man. And again, if I knew Fy, I could solve it. So my problem seems to be that I have this f of x and f of y that I need to get rid of. Well, I can put the torque here. I can put the axis here, and then I don't have to worry about them. However, something cool happens in addition to not worrying about f of x and f of y. So I still have my man, and I still have my rod weights. I have a tension here, which is T1 cos, and I have a tension here, which is T1 sine. This is going to go away. This one is at 3 meters, half the rod. This one was at 1.5 over, so 4.5 meters. And finally, the furthest one is at 6 meters. But this one here, if I try to draw my torque diagram for this guy, I get that R is 6 meters, but they're anti-parallel. The angle between them is 180, and sine of 180 is 0. So this one's not going to factor in. There's no torque due to that. Should make sense. That force is trying to push it into the wall. It's not trying to make it rotate around. Drawing my torque diagrams, I'm just going to write them like this. 3 meters, I'm RG, 4.5, I'm man G, and 6 meters, these are all my R's, T1 sine. Turn R to the force. I'm going to call these two positive and this one negative. So what I get is 0 is 3 times mRg plus 4.5 times the mass of the man G minus 6 times T1 sine theta. And I want to solve that for T1. So if I move it over, I get T1, 6 sine of 30 is equal to 3. Mass of the rod was 1450, 9.8 plus 4.5 times 90. How far away was his mass, and 9.8. If I divide through by 6 sine of 30, I get the following. The T1 is this stuff right here. So 3 times 1450 plus 4.5 times all times 9.8 divided by 6 times sine of 30. Is that right? 3 times 1450 times 9.8 plus 4.5 times 90 times 9.8 divided by 6 times sine of 30. I got a big old tension. 3 times 1450 times 9.8 times 4.5 times 90 times 9.8. My calculator is being weird. 3 times 1450 times 9.8 plus 4.5 times 90 times 9.8 divided by 6 times sine of 30, which is 15,533. 15,533 newtons is my tension. Yep. 1.55 times 10 to the 4th. Okay. They wrote it weird. And they actually 6 minus L. What are they calling their L? I don't know what they're doing with that L. It's so weird. I don't know what they're doing here. Their L is 1.5. So this ends up being 4.5. But, and they took this to be 150. I don't know why they're doing that either. They took it the other angle, or they took some other weird angle. Yeah, I don't know what angle they took from them. That's really odd. They took a really odd angle. Yeah, they used this angle. Okay. I don't know why they did that, but this is the correct answer. All right, a hollow sphere is rolling along a horizontal floor when it comes to a 34 degree incline. Now we already did this one, except I want to do it again. A hollow sphere has an I of 2/3 mr squared. Solid is 2/5. And V is 7. And our angle is 34 degrees. Now again, the energy down here is going to be mv squared over 2 plus I omega squared over 2. And the energy up here is going to be mg, this is d, sine theta, setting those two together. However, I omega squared over 2 is 2/3 mr squared times 1/2. Omega is b over r squared. The r's cancel, the 2's cancel. This becomes mv squared over 2 plus mv squared over 3. Now multiply this by 3 over 3 and this by 2 over 2, and I get 2/6 plus 3/6, I get 5/6. So I get 5/6 mv squared is mgd sine theta. They want to know how far up does it roll before it reverses direction. So d is 5/6 mv squared over mgd sine theta, no d. And my m's cancel, so ignore those. So 5/6 times b squared is 49, 7 times 7, divided by 9.8 times sine of 34. I get 7.45 meters. 7.45 exactly. So it's the exact same thing that we did before. Remember that it can roll. So the kinetic energy is linear plus rotation, but turn that rotation into mv squared with some coefficient out front. The energy at the bottom is kinetic energy. The energy at the top is potential energy of gravity, mgh, but h becomes d sine theta. And that's it for this chapter's homework. A lot of the next one we already did, so I might go a little bit faster some of them, because some of them we did already do. Some of this I did want you to do, but so first of all, for the oscillation parts, you need to remember that x of t is a cos omega t plus b. And there's a few rules about this. Omega is 2 pi over t. Omega is also 2 pi times f, because f is 1 over t. Phi is 0 if x when t is equal to 0 is a, and it's pi if x when t is equal to 0 is negative a, and phi is pi half if x when t is equal to 0 is 0. So basically how it starts. A is half of the displacement. So the max change is 2a. Or we can find in the following. So v of t is negative a sine with an omega, omega t plus b, and a of t is negative a omega squared cos negative t plus b. Now, v max happens when this is equal to 1. So v max is a omega I should do that. And A max, the maximum acceleration, is A omega squared. In this problem, we're told that an air track glider is attached to a spring, the glider is pulled to the right and released from rest. It then oscillates with a period of 2 seconds and a maximum speed of 60 centimeters per second. So period is 2 seconds. B is 60 centimeters per second, or 0.60 meters per second. We need to find A, but we need omega. So A is V over omega, and V is 0.60. Omega, remember that omega is 2 pi over T, but T is 2 seconds, so omega is pi. And that gives us pi 60, or 0.60 divided by pi is 0.19. 0.19. Put it in centimeters, it's 19. 19.1. What is the glider's position at T is equal to 0.250? So the glider is pulled to the right and released from rest. We're going to assume the following is true. Okay. So it's pulled to the right. Okay. So it's at A when T is equal to 0. That means that X is A when T is equal to 0, and therefore phi has to be 0. The reason why is X of T is A cos omega T plus phi, but if T is 0, we need phi to be something such that cosine of whatever that is equals 1. Well, cosine of 0 is equal to 1. Since this term is 0 because T is 0, and T is equal to 0, we know that phi has to also be 0. A is going to be 19.1 centimeters. All right. And omega, we said, was pi. Omega was 2 pi over T, but T was 2. So what I get is the following. X of T is A is 0.191 centimeters per meters. Cosine omega is pi times T plus 0. So that term doesn't matter, but I'm going to leave it there so you remember that it is there. Now, what we want to know is where is its position when T is 0.25. So if we let T equal 0.250, we get 0.191 cosine of 0.25 of pi, I should say, pi times 0.250. And remember, the argument has to be in radians, not degrees. That's 0.25 pi is in radians. So make sure your calculator is set correctly. Cosine of 0.25 pi. And I get 0.135 meters, or 13.5 centimeters. Okay. Just make sure you understand. Number one, we start with this equation and we need to find A, omega, and phi. We know because it was pulled all the way to the right that at T is equal to 0, it was released from its maximum amplitude, which we found in the previous part was 19.1 centimeters. We know that if it's released at time is equal to 0 from maximum A, then this equation, when T is 0, has to equal A. If that's true, phi will be 0. So we know that our phi is 0. Our phase change is 0. And so that just leaves, we found omega already. It was 2 pi over T, and T was 2 seconds. So that just leaves put the equation together and then plug in the time, which is what they did. So they plugged in the time. I don't know why they did all this junk, but that was the correct answer right there. All right. Okay, so this is reading our graph here. What is A in the equation? And A is M. A is the maximum amplitude of the cosine wave, or the distance from the center line. So it's M. What is omega? Okay. Well, omega is 2 pi over t. 2 pi over t. And then finally, phi is actually n over t times 2 pi. 2 pi n over t. The reason why is that's the phase shift. It's how far it's already gone, or omega t. Well, so you can kind of think of it as omega t. Omega is 2 pi. Omega t, yeah. Do I want to say it that way? No, just know that it's n over t. It's this distance over t, which is how far it's gone. And then you multiply that by the total. So this is a ratio of the whole thing, n over t, and the whole thing is 2 pi rads. That's probably a better way to say it. So our answer is 2 pi n over t. It's just the ratio n over t times the entire 2 pi radius. All right, so this was the ones that we had a whole bunch of different stuff to do on this one, but it's learning about this system. So the first question is, we are going to pull this to A and let it go. We're going to pull it to A and let it go. What happens? It's going to get pulled back to negative A and then start going back the other way. So it's going to move left till it hits negative A and then move back to the right. If the period is double, the frequency is, this is simply T is 1 over F. If I double this, then the frequency gets halved. Oscillating object takes 10 seconds to complete a cycle. That is, the period is 10 seconds. What is the frequency? It's 1 over 0.1. That's 100. I'm sorry, it's 10. If the frequency is 40, what is T? 1 over 40 hertz are per second. So they are a frequency. 1 over 40 is 0.25, 0.025 seconds. Which point on the axis are located at distance A from equilibrium? R and Q are both the amplitude away. The amplitude goes either way, positive or negative. Suppose that the period is T, which of the following points are separated by an interval T? The period is when it starts to repeat. So here it repeats at N. So from 0 to N would be 1. I know that's not a choice. K to P would be 1. L to whatever this would be. M would have to, M would actually be a sine wave. L would be an upside down cosine wave, L to whatever this is. K to N is an upside down sine wave, and R to N, sorry, K to P is an upside down sine wave. And R to N is a right side up cosine wave. But what they want to know is K to P, the total distance. What is the period if at time 0.005, the x coordinate of point R, so x coordinate of point R is 0.12, and the t coordinate is, the time at point K is 0.005. So it went from here to here in 0.005. That is a quarter of the whole period. The period goes from there till it repeats. This is a quarter, a quarter, a quarter, a quarter. So 4 times the time from R to K will give the full period, or 0.02. How much time does it take to travel from one point of maximum displacement to the opposite? Well, quarter, half of the period. Takes half of the period. So 0.01, the period was 0.02. What distance does the object cover during one period of oscillation? So how far does it go? We talked about this as well. this distance is A, this distance is A, and then it comes back, and this distance is A, and this distance is A. So it covers 4A. They told us our A was 0.12, so it covers 0.48. Does it cover between K and N? K to L is 1, L to M is 2, M to N is 3. It covers 3/4 of a period, or 3 times A, 0.36. All right, we did that one, so we did that one in class. Object in simple harmonic motion has an amplitude of 7.6 centimeters and a frequency of 42 hertz. At t is equal to 0, it's at its most negative. So x of t is A cos omega t plus b. We're going to talk about each of these things. So we're told that it has an amplitude of 0.076 meters. We're told that it has a frequency of 0.42 hertz. Our period is 1 over our frequency, or omega is 2 pi times our frequency. I'll just do this one then. 2 pi times 0.42. My omega is going to be 2 times pi times 0.42, 2.64 rad per second. What's wrong, babe? Stop whining. And then finally, my phase. I'm told that when t is equal to 0 is negative A. Therefore, I need x to be negative A is equal to A cosine of B when t is equal to 0. That means cosine of B has to equal -1. That means this has to be pi. So I know these 3 things. So 7.6 centimeters, that's my A. 0.84 pi is 2 times 0.42 times pi. So 0.84 pi times t minus pi. This plus and minus sign are arbitrary, which kind of sucks, but this is the only one that matches all the variables. They're not arbitrary in real life, but they're arbitrary in the problem because we don't know which way it's going or what's going on. It's at its most negative at t is equal to 0, but we got some issues there. Just trust me, it's negative pi. So I won't penalize you for having the wrong sign on the phase. In fact, I don't want you to worry about the phase right now, because what we'd have to do is figure out exactly what is going on with the velocity, and we don't need to worry about that right now. All right. Question 5. We're almost done. A spring with a constant 17 Newton per meter. A ball is attached to the spring and allowed to come to rest. It is then pulled down 2 centimeters and released, and makes 39 oscillations in 21 seconds. We want to know the mass of the ball. Okay. What we need to remember here is in the Spring equation, we have that this K, because this is MA, is minus KX. From the differential equation, we get that omega squared is K over M. So we need to find omega, and we need to find K, obviously. So M is K over omega squared. Yeah. All right. Our K is 17. We need to find omega. It makes 39 oscillations in 21 seconds. The period is the number of oscillations in the number of seconds. So this is oscillations per second. So the period is 39 divided by 21, and I get 1.857 seconds. Omega is 2 pi over t. So 2 times pi divided by that answer, I get 3.383 rad per second. And the mass, therefore, is K over omega. K was 17 divided by that answer times that answer, and I get, why am I getting something weird? Yes, this is 2 pi. Oh. No. That's really weird. That should be, yeah. Why? So that should be 17 divided by the period, but the period is 39 divided by 21, right? 1.857. So 17 times that answer divided by 4 times 5 times 5. That's really weird. I don't know why oh shoot, I am not thinking right. Periods are seconds per oscillation, so I had that flipped, and that's what I did wrong. So my omega is 21 over, yeah, I have this flipped up. It's stupid, sorry. And I should know better. Period should be in seconds. I wrote the units right, and I just messed it up. So 21 seconds per 39 oscillations. So 21 divided by 39 is 0.53846. Omega is 2 pi over t. 2 times pi divided by this answer. And then m is k, which was 17 divided by omega squared. And I get 0.125, 125 kilograms. If they want it in grams, multiply by 1,000, right? It's 125 grams. All right. What is the maximum speed? Now V max, because remember V is A omega sine. The maximum is when this is 1, so V max is A omega. We know that omega was 2 pi over t, and we know what A is, I think. The ball is allowed to come, it's pulled down 2 centimeters. So A is 0.02. Omega is 2 pi over t. So 0.2 times pi divided by 0.53846 times 0.02, and I get 23.233 meters per second is my reading. I don't know what's going on there, but they changed it to centimeters per second. I got 0.23 meters per second, which is 23 centimeters per second. Just omega A. All right, so pendulum. We just talked about this today, but the pendulum period is 2 pi I radius of gyration mg. For a simple pendulum, we're going to assume a point mass. I is mr squared. And this is r, the radius of gyration is r. So the t is 2 pi mr squared over r mg, or 2 pi r, sometimes they call it L because it's the length of the string, L over g. We're told that a pendulum has a period of 1.5 seconds. On Mars, it's 2.45 seconds, so we want g on Mars. So what we do is the period on Earth, the period on Mars. Let's square these two guys, and we end up with 4 pi squared L g on Earth, 4 pi squared L g on Mars, and that's what we're trying to find. The 4 pi squared L goes away, and what I get is Earth squared over Mars squared is equal to g on Mars, g on Earth, or g on Earth multiplied by both sides. And this is what I want to solve. So we know that G on Earth is 9.8 times the period on Earth squared, 1.5 times 1.5, divided by the period on Mars squared, 2.45 times 2.45. And you get 3.67. You just have to divide by the two of them. All right. And then we get a uniform scale bar for this one. Almost done. Our center of mass is here. This is our radius. I for a steel bar about one end is ml squared over 3. The radius of gyration is half the distance because it's the distance from the axis to the center of mass. T is 2 pi I r mg, which is 2 pi times ml squared over 3 divided by L to the half mg. L's cancel, M's cancel, one of the L's cancels. 2 goes up, which is 2L over 3G, or roundabout 1. How long is the bar? So we want to solve this. So T squared is 4 pi squared, squaring both sides, 2L over 3G. This becomes 8 pi squared over 3G, or L is 3G over 8 pi squared. And that is 3 times 9.8 divided by 8 times pi times pi. 0.372. No. What did I do wrong? 3 times 9.8 divided by 8 pi squared. Oh, I forgot the T on the other side. Times T squared. So if you do that, you get 0.95. The period is 1.6 seconds. I was just dumb. I did this right. I just forgot the T when I did everything. All right, and our final one is we have an oscillating block. We want to find the amplitude if we know the spring constant, we know the mass, and we know its velocity and its position. So let's talk about this first of all. We know that omega squared is k over m. We want to find a. So the velocity equation is a omega sine omega t plus b. We know k and we know m. And what we don't know here is we don't know what our phi is. So when t is equal to 0, we don't know what that is. I guess we'll assume, if we assume that this is, we're told, oh, we don't know t. We know that x is -5 centimeters. And we know the velocity is 19 centimeters per second. So what we can do is the following. We don't need it. I'm just being dumb. I want to show you a cool trick. And we're trying to find a. Now, if I divide this by x is equal to a cos omega t plus b. All right. These go away. This becomes V over X is equal to negative tan omega t plus phi. If I then take the arctan of both sides, arctan of V over X, negative V over X, is equal to omega t plus phi. Phi is equal to arctan of negative V over X plus omega t, where omega is equal to the square root of k over m. So let's find that first, and then we're going to find phi. So omega is k over m in the appropriate units, 2.6 Newton meters, and therefore m needs to be in kilograms, 180, so 0.180. It's in minus, you're right, sorry. I'm done. This is 2.6 divided by 0.180. I take the square root of that answer and I get 3.8. So omega is 3.8 rad per second. New page. Phi is arctan of V over X with a negative sign minus omega t. Omega was 3.8 rad per second. And t was unknown. Oh, I need to go back up for a second. I need to back up for a second. I don't want to find phi, I want to find phi plus omega t, which is arctan of negative v over x. Arctan of negative 19 centimeters per second is 0.19 meters per second over, or we could leave it in centimeters, negative 0.05 meters. The negative signs cancel. Arctan of 0.19 divided by 0.05 is 1.313473. That's what this equals. Now we know that V is equal to negative A omega sine of omega t plus phi. So we want to find A. A is equal to, move that negative over, negative B, divide through by omega sine omega t plus phi, where this stuff is that. And I get negative 0.19 meters per second over 3.8 sine of 1.313473. So A is negative 0.19 divided by 3.8 sine 1.313473. And I get, why am I getting a negative number? Something seems off here. Very strange. What am I? So if I have the mass, I know this is omega, so b squared over omega. I'm sure that what they're doing is something to do with the t. My brain is done. I think my brain just checked out on me. Because they have a squared is x squared plus b squared over omega. Why though? Where though? Oh, I'm so stupid. I know exactly what they're doing. I'm so dumb, you guys, and my brain just was trying to do this a different way. The energy at any time is the kinetic energy plus the potential energy. And the kinetic energy is mv squared over 2, and the kinetic energy is kx squared over 2. But remember that v is negative a omega sine omega t plus b, and x is a cos omega t plus b. Also remember that omega is k over m omega squared, or omega squared is k over m. Therefore, I get that the energy is m over 2 times a squared omega squared sine squared of all this plus k over 2 a squared cos squared of all this. And omega squared can be turned into k over m, so really this becomes k over 2 times a squared sine squared k over 2 a squared cos squared. But sine squared plus cos squared is 1. So energy at any time, the energy at any time is k a squared over 2. Now, because of that, I know the following is true. This is also equal to mv squared over 2 plus kx squared over 2. All right. If I want to find a squared, multiply through by 2 over k. And what I get, multiply both sides by 2 over k. What I get is 2 over k times m over 2 is m over k v squared. 2 over k cancels that. Take the square root. And what I get is this. So x is 0.05, or leave everything in centimeters, but don't do that because you're going to divide by k. Turn all the meters first. So 0.05 times 0.05, the x squared, plus m in kilograms, 180. So 0.180 kilograms divided by k, which is 2.6, multiplied by v, which is 0.19 times 0.19. And then take the square root of that answer, and you get 0.0707, or 7.07 centimeters. But this is why. Because the energy at any time is ka squared over 2, and that's mv squared over 2 plus kx squared over 2. Now, what is the maximum acceleration? Well, we can do this a couple ways, but A is a omega squared. This is the maximum acceleration because the acceleration is negative cos omega t plus b, but it's the maximum when this is 1. A, we just found, was 0.0707 meters. Omega is square root of k over m, square root of 2.6 over 0.180. So squaring that, I get that A is 0.0707 times 2.6 over 0.180. 0.0707 times 2.6 divided by 0.180. I get 1.021 meters per second squared. Or 1.2 102 centimeters per second squared. They rounded it down to 100. What is the block position when its acceleration is maximum? When its acceleration is at a maximum, it has to either be all the way compressed or all the way stretched. When is it 0? when it's in the center, when it's at x is 0. So whatever our A was, it's at negative 7.1. It has to be at the negative amplitude. What is the speed of the block when it's at x is 3.0 centimeters? So this one, Ka squared over 2 is the maximum energy, mv squared over 2 plus kx squared over 2. mv squared over 2 is Ka squared over 2 plus, minus kx squared over 2. We want to find v. So v squared multiplied through by 2 over m. I get k over m times a squared minus k over m times x squared, or taking the square root, but this is omega squared. So what I get is, I get that v is the square root of omega squared a squared minus omega squared x squared. And remember that our omega was what, 3.8? No, our omega was, the square root of 2.6 divided by 0.180. Yeah, 3.8. So our omega is 3.8 rad per second. And our A was 0.0707 meters. And our X is given to us here as 3 centimeters. So 3.8 times 3.8 times 0.0707 times 0.0707 minus 3.8 times 3.8 times 0.03 times 0.03. Square root of that answer, and I get 0.243 or 24.3 centimeters per second. 24 centimeters per second. All right. So this one's all about using the energy equation. This is the total energy at any time. This is the particular kinetic energy and the particular potential energy of the spring. Other than that, cool. We're done with this. I recorded this. It should, I don't know, take half an hour, maybe an hour to upload and then be done. I'm going to post in a little bit. Actually, I'll post it tomorrow morning. If I don't post it tonight, I might post it tomorrow morning. I'm actually wiped out. The solution to the practice exam will go up tomorrow morning. So anyway, thank you all for coming. I'll see you guys Friday. We're going to review the problems on the practice exam, and your grades should be up by noon tomorrow, so you'll know how you did on exam 3, and you'll know if you really want to take the final. But otherwise, I'll see you Friday.